Okay, good morning. Today I'm going to work on the sample problems that were discussed at the end of my lecture on IV Bolus One Compartment model. And we went over some of the problems in detail, but some of the other problems I just mentioned how to approach and how to solve without working on a problem myself and asked you guys to work on the problems. So I'm going to just record the entire set of problems, these sample problems that were posted through Echo 360. So the first problem is that of cephalosporin antibiotic. The dose was 500 milligrams, and given as an IV bolus to a female patient, 63 years, body weight equals 55 kilograms. The volume of distribution is equal to 0.1 liters per kilogram, and so times 55 kilograms is going to be equal to 5.5 liters. The t-half is given as 0.75 hours. So from this you can actually calculate the KEL. Because it's one compartment open model, the KEL is going to be 0.693 divided by t-half, which is equal to 0.693 divided by 0.75. 0.924. The unit is per hour. And what is being asked is, the first question is the plasma concentration immediately after the injection, which is C0. That's what they're asking us to calculate. So we know one way to do this is excuse me. We know that volume of distribution is equal to dose divided by C0. So from here, we can solve for C0 as being equal to dose divided by volume of distribution, in which case we have 500 milligrams divided by the volume of distribution is 5.5 liters. So that is going to be equal to 90.9 milligrams per liter. So that is your C0. So the next part of the problem is to calculate the amount in the body 4 hours after the dose was given. So it's a single dose. So we know that the equation that we need to use is, it's a first order model. So the equation that connects the plasma levels is Ct, which is a plasma level at any time t, is C0, which is a plasma level at time 0, e raised to negative KEL times t. Now the amount of drug at any time t, xt, is going to be equal to x sub 0 e raised to negative KEL times t. So what is being asked here is to calculate the amount of drug in the body 4 hours after the dose. So to calculate that, we know x sub 0, which is a dose, is 500 milligrams times e raised to negative KEL. KEL we calculated as 0.924 and the time is 4 hours after the dose. So that's your t, and now you can use your calculator. It's 12.4 milligrams. Okay, so that's the amount of drug in the body 4 hours after the dose was given. Now the next part of the question is to calculate how much time it will take for the level to go down to 0.5 micrograms per ml. So CT is given as 0.5 micrograms per ml. Now, 0.5 micrograms per ml is the same as 0.5 milligrams per liter. Because we have to make sure that the units that we are using is consistent. This is very important. You can easily make mistakes. You have to have consistent units across all the terms that you're using in the equation. So here's in milligrams per liter. This has to be in milligrams per liter. Make sure that, you know, this is all properly converted and accounted for when you do the math. So what is given is 0.5. I'm going to ignore the units when I write down this equation, or maybe I can just write it out, is equal to C0 was 90.9 times e raised to negative 0.924 times t. It is this t that we're trying to determine. How much time does it take for the level to fall to 0.5? You know, that's one way of writing in the exponential format. You can also write this in the linear form. Natural log of 0.5 is equal to natural log of 90.9 minus 0.924 t. So now if you solve for t, t is going to be equal to natural log of 90.9 minus natural log of 0.5, the whole thing divided by 0.924. So 5.6 hours. So it'll take 5.6 hours for the plasma level to fall down to 0.5 micrograms per milliliter. So that was the first sample problem. You know, there were 3 parts to it. The next sample problem was a data table that was given. The dose was given as 80 milligrams. And the first part was to calculate KEL using linear regression. And at this point, I'm going to ask you to refer back to the math review video. There I discuss how to do linear regression for our first order problem. In this case, what we have to do is, go into the statistics mode. And then for x, you will enter time, 0.5, 1, 2, 4, 8, etc. And for y, you have to enter natural log of this concentration that is given in the table. So natural log of 6, natural log of 5.3, etc. So once you go into the statistics mode, and again, remember to clear the data. And then, after clearing the data, go into the 2 variable statistics mode. And enter data. X1 is 0.5. Y1 is natural log of 6. X2 is 1. Y2 is natural log of 5.3. X3 is 2. Y3 is natural log of 4.2. X4 is 4. Y4 is natural log of 2.6. X5 is 8. Y5 is natural log of 1. And you click stat var, and you'll get the numbers that you're looking for. So the first, as you scroll through the data that you get when you do the linear regression, if you highlight, lowercase a, that is your slope, and it is given as negative 0.238 and so on. I'm going to round it to 3 decimal places, so it's 0.239. Excuse me. So we know that then KEL is 0.239 since the time that we entered was in hours. So this is going to be per hour. So KEL is 0.239, and if you scroll once to the right again, you'll get B, which is the intercept, 1.90996, and that's your intercept. But that is actually, since everything is y, that's a y-intercept. So because we entered y as a natural log in order to get, so this is actually natural log of C0. In order to calculate C0, then what we need to do is e raised to 1.90996. It is, if you round it to 1 decimal place, the number is 6.8 milligrams per liter is a unit that we used. And so that's your KEL, and we calculated the C0 using linear regression in this manner. Now, the next part of the problem is to calculate the AUC using the trapezoidal rule. So AUC 0 to infinity. So again, we have to go back and start with the trapezoid, the area. If you look back in my notes, it's basically subdividing the plasma level versus time curve into trapezoids, calculating the individual areas of the trapezoids and adding all of those trapezoidal elements together with the terminal area, which is defined as C last divided by KEL. So I'm going to just graphically draw that here and then write it out. So we have C0, that is 6.8, and then, the first is there, that is 6, and then you have 5.3, then you have 4.2, then you have 2.6, and C last is 1. Not drawn to scale, but just to show this continues to exponentially decrease like that. Use a different color. Okay. So the AUC is basically that trapezoid plus that trapezoid plus that trapezoid plus that trapezoid plus that trapezoid, and then the terminal area that keeps going like that. So the AUC is the area of the trapezoid is basically the average. Let me write the time points here as well. So that is 0, 0.5. Again, this is not to scale, just exaggerated so that you'll understand what's going on. 1, 2, 4, 8, and that goes to infinity. So the area of the first trapezoid is going to be basically the average of the mean of these sides, right? 6.8 and 6. Basically 6.8 plus 6 divided by 2 times the time difference. So 0 minus 0.5, or I can write 0.5 minus 0. The next trapezoidal element is the average of the next two sides, 6 plus 5.3 divided by 2. So the average of the concentrations, two consecutive concentrations times the time difference, that's all, times 1 minus 0.5. The third trapezoid is 5.3 plus 4.2 divided by 2 times 2 minus 1 plus 4.2 plus 2.6 divided by 2 times 4 minus 2, which is the time difference, plus 2.6 plus 1 divided by 2 times 8 minus 4, and the C last, which is 1, divided by KEL that we calculated earlier, 0.239. So let's do the math. 6.8 plus 6 divided by 2 times 0.5, 3.2 plus 6 plus 5.3 divided by 2 times 0.5, 2.825 plus, I'm going to keep all the decimal places for the time being, and I'm going to round it at the end. Next is 4.75. $6.8. $7.2. $4.184. You add all that together, $28.959. And if you round it, try to round it to one decimal place, it's going to be 29. Right? 29 milligrams hours later is -1. So that's your AUC 0 to infinity. Now the next part, so just to remember here is the trapezoidal elements, average of the concentrations times the time difference. Make sure that everything's correct, enter the data properly, and do the math, basically simply adding all the AUC elements together with the C last divided by KEL, and you'll get the final answer. Now the next part is to calculate the AUC using the equation C0 divided by KEL. We calculated C0 as 6.8 milligrams per liter, and the KEL is 0.239 per hour. So let's see what we're going to get. Is 28 point, if you round it to one decimal place, it's 28.5, again, milligrams hours per liter. So pretty close when you use the equation as well as the trapezoidal method. So I'll just put that in there so that you'll know. how these two numbers compare. Okay, so that is that problem. And the next sample problem, number 3, was an antibiotic that is given, and the levels were determined 2 hours and 5 hours after the dose was given as an IV bolus, and the plasma concentrations or the drug concentration, the levels were 1.2 and 0.3. So if you just time in hours and CT in micrograms per ml. So 2 hours after the dose, the level was 1.2 micrograms. 5 hours after the dose is given, the level was 0.3. So the first part of the problem is to calculate the KEL. So again, you can use the linear form, which is natural log of Ct is equal to natural log of C0 minus KEL times T. Which can be adapted to this as natural log of C2 is equal to natural log of C1 minus KEL times T2 minus T1. Do that too. So in this case, natural log of 0.3 is equal to natural log of 1.2 minus KEL times 5 minus 2. And if you solve for KEL, it's going to be natural log of 1.2 minus natural log of 0.3. The whole thing divided by 5 minus 2 is 3. So natural log of 1.2 minus natural log of 0.3 divided by 3 is 0.462. Again, what's the unit? Per hour. The next thing is to calculate the half-life. We know for a one compartment open model, T half is equal to 0.693 divided by KEL, which is 0.693 divided by 0.462. Is 1.5 hours, unit hour. So that's the half-life. And that's a KEL. Then there's sample problem number 4. For this drug, for this example, half-life is given as 8 hours. So then you can immediately calculate the KEL from this information, 0.693 divided by 8. And if you round it to 3 decimal places, it's going to be 0.087. Again, unit is per hour. The dose that is given is 600 milligrams. So x sub 0 is 600 milligrams. The volume of distribution is given as 400 milliliters per kilogram, and the patient's weight is 62 kilograms. So then the volume of distribution will be 400 milliliters per kilograms times 62 kilograms, which is 24,800 milliliters. If we convert that into liters, it's 24.8 liters. So we have calculated the KEL, we have the volume of distribution, we have dose, we have half-life. We can calculate all of this information from whatever is given in the problem. Now, the actual question is to calculate what percent of the dose is eliminated in 24 hours. So at t is equal to 24 hours, what percent of the dose is eliminated? Now, the fraction eliminated at time t, this is from the basic equation, first order equation, of fraction eliminated in time t is actually equal to e raised to negative KEL times t. So here t is given as 24 hours, so all we have to do is calculate e raised to negative 0.087 times 24. Which is going to be equal to 0.12 if you round it to 4 decimal places, 0.124. Sorry, I made a mistake here. This is not fraction eliminated, fraction remaining. In time t is e raised to negative KEL t. That's why you just multiply that with the C0 or plasma level times 0, and you'll get the plasma level at any time t. So that's fraction remaining. Please make sure that you correct that. It's fraction remaining. Okay, so that's the fraction remaining. So what is the fraction eliminated? Equals 1 minus 0.124. Is 0.876. So then percent eliminated is 0.876 times 100 is equal to 87.6%. So that's the answer to that question. 87.6 of the dose is eliminated. So the next part of the problem is what is the expected plasma drug concentration of 24 hours post-dose? So to do that, we need to calculate C0, which can be done based on dose divided by volume of distribution. The dose is 600 milligrams, and the volume of distribution was 24.8 liters. So basically 600 divided by 24.8. If you round it to one decimal place, it's going to be 24.1. Sorry, 24.2 milligrams per liter. So that's 24.2 milligrams per liter, and that's a C0. Now CT is C0 times e raised to negative KEL times T, and we already calculated e raised to negative KELT is 0.124. So that is going to be 24.2 times 0.124 is 3 milligrams per liter. Okay, so that's your plasma level at 24 hours. Okay, now the next problem has several small subtopics. So this was sample problem number 4, sample problem number 5. A compound is given as an IV bolus injection to a patient requiring a minimal plasma concentration of 4 milligrams per liter for a therapeutic effect. Given that the dose is equal to 100 milligrams, KL is 0.1 per hour, and V is 8 liters. Assume one compartment model. Calculate how long the clinical effect is expected to last with this dose. So basically, if you take the plasma level versus time curve, that's C0, and that's your minimum effective concentration. That is T is equal to 0, and that is T. What we are trying to calculate here is how much time does it take for the plasma level to drop from C0 to that. How can we calculate the C0? Because we are given enough information to do that. First of all, we know the MEC, which for making things easier, I'm going to call it C sub T, is 4 milligrams per liter. You have the dose at this point is 100 milligrams. The KEL is given as 0.1 per hour. And the volume of distribution is 8 liters. So C0 is going to be equal to X sub 0 divided by V, which is 100 milligrams divided by 8 liters, 12.5 milligrams per liter. Again, you can use a linear form of the equation, natural log of 4 is equal to natural log of 12.5 minus KEL is given as 0.1 times T. How long does it take for the plasma level to fall from 12.5 to 4? That's what we're trying to calculate. So solving for T, natural log of 12.5 minus natural log of 4 divided by 0.1. That is how long it will take. So if you round it to 1 decimal place, it's going to take 11.4 hours. So that's how much time you can expect for the effect to be present. So the next part of the problem is now the dose is increased to 200 milligrams. So dose increased 2 times, which is basically 200 milligrams. So does the volume of distribution change? No, it doesn't change. It's still going to be 8 liters. But is the C0 going to change? Of course it's going to change, because now you have twice the amount of drug in the body, so 200 milligrams divided by 8 liters. Is 25 milligrams per liter. So you see the plasma level is going to be proportional, directly proportional to the dose. Twice the amount, twice the level, twice the amount led to twice the level. Now let's see how long would it take for the effect to last if the dose was doubled. So here again, CT is not going to change. The minimum effective concentration is 4 milligrams per liter, so natural log of 4 is still going to be equal to natural log of 25 minus 0.1 times T, and you're solving for T. So natural log of 25 minus natural log of 4, the whole thing divided by 0.1. If you round it to 1 decimal place, it's 18.3 hours. So definitely the duration of effect is increasing, but doesn't double, obviously, because the levels are connected through the logarithmic relationship. Now let's see what will happen you have the KEL is changing. So now, in the next part of the problem, the dose is 100 milligrams. Volume of distribution is 8 liters. But the KEL decreased. KEL halved, actually. And the change in KEL in this instance is due to a 2 times decrease in clearance. So let's see what is going to happen to the duration there. Everything else remains the same from that first problem, except for that, we're still solving for t, natural log of 12.5 minus natural log of 4, the whole thing divided by, instead of 0.1, it's going to be 0.05. So now the duration is, if you again round it to 1 decimal place, it's 22.8 hours. So if you compare the first duration when the elimination was not changed in 0.1 to now, the duration has almost doubled for a change in KEL and in this example the KEL decreased because there is a twofold decrease in clearance. Now the next part of the problem is really interesting because here again we have the dose is 100 milligrams, KEL is halved, but this change in KEL is not due to a change in clearance, but rather doubling of the volume of distribution. So now we know then that, because the volume of distribution is given as 8 liters, the original volume of distribution is 8 liters. Now when it is doubled, it's going to be equal to 2 is 16 liters. So now the volume of distribution has changed. So now because the volume of distribution has changed, that is going to impact your peak. So C0 is equal to 100 milligrams divided by 16 liters. Is 6. If you round it to 1 decimal place, it's 6.3 milligrams per liter. So now let's calculate the duration. Again, T is going to be equal to natural log of 6.3 minus natural log of 4, the minimum effective concentration still is 4, divided by 0.05. That's 9.1 hours. So obviously there is a big difference when the KEL is changed for different reasons. If the KEL is impacted, again, this was mentioned earlier, maybe during the lecture, how volume of distribution and clearance can change independently of each other. And this problem clearly demonstrates that these can independently change, and when they change, how they impact the pharmacokinetics in entirely different manner. When the KEL changed because there's a decrease in clearance, the duration increased, which is expected. But when the KEL changed because of an increase in volume of distribution, because now this impacted the peak level, that is going to have an impact on the duration of effect, and the effect is going to be a lowering, or the duration is going to be lower. So that is what is being discussed as part of the next part of the question, with the question asking, does doubling the dose of the drug under the initial conditions yield the same change in duration of clinical effect as doubling the half-life? So you can review the math that was done and the discussion I just gave and come to a conclusion on that aspect of the problem. With that, I'm going to stop. So this should cover all the sample problems that were posted on ECHO 360 related to the one compartment model for the IV bolus injection. So review this video, work on the practice problems, the homework problems that is, and if there are still any questions, let me know. Thank you.